Hey everybody. Today we're talking about complex numbers. We're going to learn how to add, subtract, multiply, and divide them. Our motivation for complex numbers comes from this equation, x squared plus 1 equals 0, which has no real solution. You can see that by subtracting 1 from both sides. There's no real number whose square is negative 1, or any other negative number for that matter. Mathematicians get around that problem by just defining a solution. Let's let I, the imaginary unit, be defined to be the square root of negative 1. Right away, we can see that I squared is negative 1, so I is going to satisfy this equation. Multiplying by I again, by the way, we can see that I cubed is negative I to the fourth is 1, and so on. I to the fifth is I, and I to the sixth is negative 1. In particular, when you're doing powers of I, if the power is a multiple of 4, you get 1 back. If the power is 1 more than a multiple of 4, you get I back, and so on. If we add a real number and an imaginary number, we get what we call a complex number, something of the form a plus bi, where a and b are both real numbers. A gets called the real part, and b gets called the imaginary part. Here's a few examples of complex numbers. 4 minus 3i, the real part is 4, and the imaginary part is negative 3. Pi plus 10i. 8i, a purely imaginary number, is also a complex number, 0 plus 8i. Similarly, the real number 3 also gets considered a complex number, because that's 3 plus 0i. We add and subtract complex numbers just by adding and subtracting like terms, adding and subtracting the real and imaginary parts. For instance, 4 minus 3i plus negative 2 plus 9i is 2 plus 6i. I've taken the real parts, 4 plus negative 2, and gotten 2, and the imaginary parts, negative 3i plus 9i, and gotten 6i. 2i minus, parenthesis, 1 plus 2i, is going to be 2i minus 1 minus 2i, distributing that negative sign. Simplifying, I get negative 1. Here, by the way, when I subtracted two complex numbers, I got a real number back. That can happen. We multiply complex numbers just by distributing and simplifying. For instance, 3 times 7 minus I is 21 minus 3i. And 4i times 2 plus 9i is 8i plus 36i squared. Now, this last expression can be simplified because I squared is negative 1. So we can rewrite it in standard form, negative 36 plus 8i. When you're doing multiplication or other operations with complex numbers, you should always finish up with something in standard form, a plus bi. Let's do a couple of slightly harder multiplications. 3 minus 3i times 1 minus 4i. So I distribute, first outside, inside, last. And then I'm going to combine the negative 3i and the negative 12i to get negative 15i, and replace the I squared with negative 1. Finally, taking 3 minus 12, I get negative 9 for my real part. Here's my final answer in standard form. Example 2, 6 plus 2i times 6 minus 2i. Again, I FOIL and combine like terms, replacing the I squared with negative 1. Overall, I get 36 plus 4, or 40. Here, when I multiplied two complex numbers, I got a real number back. Also notice, in both of these cases, I did not forget to simplify my answer to get something in standard form at the end. So this last example, 6 plus 2i times 6 minus 2i equals 40, is illustrating a common situation. We're multiplying two things of the form a plus bi times a minus bi. And whenever we do that, we get a real number back. Just by distributing, combining like terms, and replacing I squared with negative 1, we're always getting a squared plus b squared. This phenomenon leads us to this definition. The numbers a plus bi and a minus bi are called complex conjugates of one another, and their product is always going to be real. The product of complex conjugates is the sum of the squares of the real and imaginary parts. By the way, the sum of complex conjugates is always real. A plus bi and a minus bi have a sum of 2a. Those two facts are very useful. We can use complex conjugates to do division of complex numbers, something that we haven't been able to do up till now. The idea is just to take the denominator, take its complex conjugate, and then multiply that conjugate by both the numerator and denominator. This is helpful because we know that that denominator is going to be real. In particular, we know that the denominator is going to be the sum of the squares of the real and imaginary parts, 4 squared plus 2 squared. The numerator, I have to FOIL like usual, just doing my regular complex multiplication. I'm going to combine like terms in that numerator, replacing I squared with -1 as I go. Overall, I get 2 plus 16i over 20, or 1/10 plus 4/5 I, to write it completely in standard form. Let's do one more like this. 4 plus 2i divided by 2 minus 5i. Again, I take the conjugate of the denominator and multiply that by both the numerator and denominator. This is going to make the denominator real. I get 2 squared plus 5 squared in the denominator. In the numerator, I FOIL, combine like terms, and replace the I squared with -1. Overall, I get -2/29 plus I. Complex numbers come up very frequently when we're dealing with quadratic equations. Things of the form ax squared plus bx plus c equals 0. And quadratic equations like this frequently have complex roots. So remember, we can always solve a quadratic equation in this form using the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. The quantity b squared minus 4ac, the thing inside the radical, is called the discriminant of the quadratic. And the reason it gets called that is that if it's positive, then that square root is going to exist. It's going to be a real number. And we're going to get two distinct real roots. If that discriminant is equal to 0, so the radical is equal to 0, the plus minus is a plus minus 0, and so I'm only getting one real root, which is repeated. Finally, if that discriminant is negative, I get two complex roots. And it turns out that they're complex conjugates of one another. So both the product and sum of the roots of a quadratic equation are both going to be real. Here's an example. Solve 3x squared minus 2x plus 4 equals 0. We're going to use the quadratic formula. Plugging in a equals 3, b equals -2, and c equals 4, we get this, which simplifies to 2 plus or minus the square root of -44 over 6. So the square root of -44 is the square root of 44 times the square root of -1, or root 44 times I. Now, that square root of 44 has a square factor in it, namely 4, which I'm going to factor out. Square root of 4 is 2. So 2 plus or minus 2 root 11 times I over 6. Canceling out that 2 and writing this in standard form, I get 1/3 plus or minus the square root of 11 over 3 times I. That's going to be the two answers to this quadratic formula, or to this quadratic equation. And you can clearly see that they're conjugates of one another. For practice, I encourage you to take each of those solutions and plug them back into this equation and verify that when you plug into the left-hand side, you really do get 0.